Welcome to aminacademy.com. Let us do mini tour on chemistry. That means we have to do history of chemistry. The history of chemistry represents a time span from ancient history to the present. By 1000 BC, civilization used technologies that would eventually form the basis of the various branches of chemistry. Examples include the discovery of fire, extracting metals from ores, making pottery and glazes, fermenting beer and wine, extracting chemicals from plants for medicine and perfumes, rendering fat into soap, making glass, and making alloys like bronze. The protoscience of chemistry, alchemy, was unsuccessful in explaining the nature of matter and in transformations. Early metallurgy. The earliest recorded metal employed by humans seems to be gold, which can be found free or native. Some small amounts of natural gold have been found in Spanish caves used during the late Paleolithic period around 40,000 BC. Silver, copper, tin and meteoric iron can also be found native, allowing a limited amount of metalworking in ancient cultures. Egyptian weapons made from meteoric iron in about 3000 BC were highly prized as daggers from heaven. Arguably, the first chemical reaction used in controlled manner was fire. Bronze Age. First evidence of this extractive metallurgy dates from the 6th and 5th millennia BC and was found in the archaeological sites of the Winsa culture. These first metals were single elements or else combination as naturally occurred. By combining copper and tin, a superior metal could be made, an alloy called bronze. This was a major technological shift that began the Bronze Age about 3500 BC. After the Bronze Age, the history of metallurgy was marked by armies seeking better weaponry. Iron Age. The extraction of iron from its ore into a workable metal is much more difficult than copper or tin. While iron is not better suited for tools than bronze until steel was discovered. Iron ore is much more abundant and common than either copper or tin, and therefore more often available locally with no need to trade for it. The Iron Age refers to the advent of iron working, that is ferrous metallurgy. Historical developments in ferrous metallurgy can be found in a wide variety of past culture and civilization. Democritus, a Greek philosopher and ancient alchemist. Philosophical attempt to rationalize why different substances have different properties, color, density, smell, exist in different states, gaseous, liquid and solid, and react in the different manner when exposed to environments. For example, to water or fire or temperature changes led ancient philosophers to postulate the first theories on nature and chemistry. In ancient world, around 420 BC, Empedocles states that all matter is made up of four element substances: earth, fire, air and water. The early theory of atomism can be traced back to ancient Greece and ancient India. Greek atomism was made popular by the Greek philosopher Democritus, who declared that matter is composed of invisible, indivisible and indestructible particles called atomos around 380 BC. Earlier, Leucippus also declared that atoms were the most indivisible part of the matter. This coincided with a similar declaration. Medieval alchemy. 15th century artistic impression of Jabir ibn Hayyan, Jaber, a Perso-Arab alchemist and pioneer in organic chemistry. What is alchemy? A form of speculative thought that, among other aims, tried to transform base metals such as lead or copper into silver or gold, and to discover a cure for disease and a way of extending life. Arab alchemist Jabir ibn Hayyan and was rooted in the classical elements of Greek tradition. Chemistry share an interest in composition, and alchemy and chemistry share an interest in the composition and properties of matter, and until the 18th century they were not separate disciplines. The term chemistry has been used to describe the blend of alchemy and chemistry that existed before that time. Alchemy in the Islamic world. In the Islamic world, the Muslims were translating the work of ancient Greek and Hellenistic philosophers into Arabic, and were experimenting with scientific ideas. The Arabic works attributed to the 8th century alchemist Jabir ibn Hayyan introduced a systematic classification of chemical substances and provided instructions for deriving an inorganic compound, sal ammoniac, ammonium chloride, from organic substances such as plant, blood and hair by chemical means. Problem encountered with alchemy. There are several problems with alchemy as seen from today's standpoint. There was no systematic naming scheme for new compounds, and language was esoteric and vague to the point that the terminologies mean different things to different people. In 17th and 18th century early chemistry, practical attempts to improve the refining of ores and their extraction to smelt metals was an important source of information for early chemists in the 16th century, among them George Agricola, who published his great work De Re Metallica in 1556. His work describes the highly developed and complex process of mining metal ores, metal extraction and metallurgy of the time. Jean-Baptiste van Helmont suggested that there are substantial substances other than air and coined a name for them, gas, from the Greek word chaos. In addition to introducing the word gas into the vocabulary of scientists, Van Helmont conducted several experiments involving gases. Anglo-Irish chemist Robert Boyle is considered to have initiated the gradual separation of chemistry from alchemy. The law describes the inversely proportional. The Boyle's law tells that it describes the inversely proportional relationship between the absolute pressure and volume of gas if the temperature is kept constant within a closed system. This is a Boyle's law. Through his work, Boyle helped to lay the foundation for the chemical revolution 2 centuries later. Joseph Priestley, co-discoverer of the element oxygen, which is called dephlogisticated air. In 1702, German chemist George Stahl coined the name phlogiston for the substance believed to be released in the process of burning. In 1754, Scottish chemist Joseph Black isolated carbon dioxide, which he called fixed air. Cavendish discovered the hydrogen as a colorless, odorless gas, burns and can form an explosive mixture with air, and published a paper on the production of water by burning inflammable air, that is hydrogen, in dephlogisticated air, now known to be oxygen, the latter a constituent of atmospheric air, phlogiston theory. In 1781, Carl Wilhelm Scheele discovered the new acid, tungstic acid, that is called tungstic acid, could be made from constant scheelite, at the time named tungsten. A voltaic pipe on display in the Tempio Voltiano, the Volta Temple, near Volta home in Como. Italian physicist Alessandro Volta constructed a device for accumulating a large charge by series of induction and grounding. In 1800, Volta stacked several pairs of alternating copper or silver and zinc disc electrodes separated by cloth or cardboard soaked in brine, that is electrolyte, to increase the electrolyte conductivity. When the top and bottom contact were connected by a wire, an electric current flowed through this voltaic pipe and the connecting wire. Thus, Volta is credited with constructing the first electrical battery to produce electricity. This Volta is considered to be the founder of the discipline of electrochemistry. A galvanic cell, that is voltaic cell, is an electrochemical cell that derives electrical energy from a spontaneous redox reaction taking place within the cell, and generally consists of two different metals connected by a salt bridge or individual half cells separated by a porous membrane. Anthony Laurent de Lavoisier demonstrated with careful measurements that transmutation of water to earth was not possible, but the sediment absorbed from the boiling water came from the container. He burnt phosphorus and sulfur in air and proved that the product weighed more than the original samples, with the mass gained being lost from the air. Thus, in 1789, he established the law of conservation of mass, which is also called Lavoisier's law. The world's first ice calorimeter, used in the winter of 1782 by Anthony Lavoisier and Pierre Simon Laplace to determine the heat involved in various chemical changes, calculations which were based on Joseph Black's prior discovery of latent heat. These experiments marked the foundation of thermochemistry. Lavoisier worked with Claude-Louis Berthollet and others to devise a system of chemical nomenclature which serves as the basis of modern system of naming chemical compounds. With Pierre Simon Laplace, Lavoisier used the calorimeter to estimate the heat evolved per unit of carbon dioxide produced. The revolution in chemistry which he brought about was a result of conscious effort to fit all experiments into the framework of a single theory. In 1802, French-American chemist and industrialist Eleuthery Irency Dupont, who learned manufacture of gunpowder and explosive under Anthony Lavoisier, founded a gunpowder manufacturer in Delaware known as A.I. Dupont de Nemours and Company. Michael Faraday was another early worker whose major contribution to chemistry was electrochemistry, in which, among other things, a certain quantity of electricity during electrolysis or electrodeposition of metals was shown to be associated with certain quantities of chemical elements and fixed quantities of the elements, therefore, with each other in specific ratios. Vladimir Markovnikov, born 1838, was a Russian scientist who proceeded most of his work at Kazan University in Russia. In his time at the university, he studied a laboratory better known as the cradle of Russian organic chemistry. John Dalton. In 1803, English meteorologist and chemist John Dalton proposed Dalton's law, which describes the relationship between the components in a mixture of gases and the relative pressure each contributes to the overall mixture. Discovered in 1801, this concept is also known as Dalton's law of partial pressure. Dalton also proposed a modern atomic theory in 1803, which stated that all matter was composed of small indivisible particles termed atoms. Atoms of a given element possess unique characteristics and weight, and three types of atoms exist: simple elements, compound, simple molecules, and complex molecules. In 1808, Dalton first published a new system of chemical philosophy, in which he outlined the first modern scientific description of the atomic theory. This work identified chemical elements as a specific type of atom, therefore rejecting Newton's theory of chemical affinities. Instead, Dalton inferred proportions of elements in compounds by taking ratios of the weights of the reactant, setting the atomic weight of hydrogen to be identically 1. Following the Jeremias Benjamin Richter, known for introducing the term stoichiometry, he proposed that chemical elements combine in integral ratios. This is known as the law of multiple proportion, or Dalton's law. The Swedish chemist and disciples of Dalton, Johannes Jacob Berzelius, embarked on a systematic program to try to make accurate and precise quantitative measurements and to ensure the purity of chemicals. English chemist Humphrey Davy was a pioneer in the field of electrolysis, using Alessandro Volta's voltaic pile to split up common compounds and thus isolate a series of new elements. He went on to electrolyze molten salts and discovered several new metals, especially sodium and potassium, highly reactive elements known as the alkali metals. Potassium, the first metal that was isolated by electrolysis, was discovered in 1807 by Humphrey Davy, who derived it from caustic potash, that is KOH. Joseph Louis Gay Lucas. He concluded that equal volumes of all gases expand equally with the same increase in temperature. This conclusion is usually called Charles' law, as Gay Lucas gave credit to Jacques Charles, who had arrived at nearly the same conclusion in the 1780 but had not published it. Gases at constant temperature and pressure combine in simple numerical proportion by volume, and the resulting product or products if gases also bear a simple proportion by volumes to the volumes of the reactant. In other words, gases under equal conditions of temperature and pressure react with one another in volume ratios of small whole numbers. This conclusion subsequently became known as Gay-Lucas law, or the law of combining volumes. Amedeo Avogadro, who postulated that under controlled conditions of temperature and pressure, equal volumes of gases contain an equal number of molecules. This is known as Avogadro's law. A paper that suggested a way out of this, Avogadro, who hypothesized that equal volumes of gas at the same temperature and pressure contain equal number of molecules, from which it followed that relative molecular weights of any two gases are the same as the ratio of the densities of the two gases under the same condition of temperature and pressure. Euler and the vitalism debate. In 1825, Friedrich Euler and Justus von Liebig performed the first confirmed discovery and explanation of isomers, early named by Berzelius. Discovery of the artificial synthesis of urea contributed greatly to the theory of isomerism, as the empirical chemical formulas for urea and ammonium cyanide are identical. Liebig is considered the father of the fertilizer industry for his discovery of nitrogen as an essential plant nutrient, and his formulation of the law of the minimum, which described the effect of individual nutrients on crops. Mid-18th. In 1840, German Hess proposed Hess law, an early statement of the law of conservation of energy, which established that energy changes in a chemical process depend only on the state of the starting and product materials and not on the specific pathway taken between the two states. Formulas of acetic acid given by August Kekulé in 1861. The real breakthrough came with the International Chemical Congress held in the German town of Karlsruhe in September 1860, at which most of the leading European chemists were present. Carbon forming exactly four chemicals bond could link together to form what he called a carbon chain or carbon skeleton, to which the other atoms with other valence such as hydrogen, oxygen, nitrogen and chlorine could join. A Crookes tube. A light and dark, electrons travel in straight line from the cathode left, and evidenced by the shadow cast from the Maltese cross on the fluorescence of the right hand end, and anode is at the bottom wire. British chemist and physicist William Crookes is noted for his cathode ray studies, fundamental in the development of atomic physics. His researches on electrical discharges through rarefield gas led him to observe the dark space around the cathode, now called the Crookes dark space. He demonstrated that cathode ray travel in straight lines and produce phosphorescence and heat when they strike certain materials. A pioneer of vacuum tubes, Crookes invented the Crookes tube, an early experimental discharge tube with partial vacuum, with which he studied the behavior of cathode rays. Swedish chemist and inventor Alfred Nobel found that when nitroglycerin was incorporated in an absorbent inert substance like Kieselguhr diatomaceous earth, it becomes safer and more convenient to handle, and this mixture he patented in 1867 as dynamite. Nobel later on combined nitroglycerin with various nitrocellulose compounds similar to collodion, but settled on a more efficient recipe combining another nitrate explosive and obtained a transparent jelly-like substance, which was a more powerful explosive than dynamite. An important breakthrough in making sense of the list of known chemical elements as well as in understanding the internal structure of atoms was Dmitri Mendeleev. Development of the first modern periodic table, or the periodic classification of the elements. Mendeleev, a Russian chemist, felt that there was some type of order to the element, and he spent more than 13 years of his life collecting data and assembling the concepts, initially with the idea of resolving some of the disorder in the field for his student. Mendeleev found that when all the known chemical elements were arranged in order of increasing atomic weight, the resulting table displayed a recurring pattern or periodicity of properties within group of elements. Mendeleev's law allowed him to build up a systematic periodic table of all the 66 elements then known based on atomic mass, which he published in Principles of Chemistry in 1869. His first periodic table was compiled on the basis of arranging the elements in ascending order of atomic weight and grouping them by similarity of properties. J. Willard Gibbs formulated a concept of thermodynamic equilibrium of a system in terms of energy and entropy. He also did extensive work on chemical equilibrium and equilibria between phases. American mathematical physicist J. Willard Gibbs' work on the application of thermodynamics was instrumental in transforming physical chemistry into a rigorous deductive science. Gibbs took all of the variables involved in a chemical reaction: temperature, pressure, energy, volume, and entropy, and included them in one simple equation known as Gibbs phase rule. Together with Boltzmann and James Clerk Maxwell, Gibbs created a new branch of theoretical physics called statistical mechanics, a term that he coined. Late 19th century. German engineer Carl von Lindes Invention of a continuous process of liquefying gases in large quantities formed a basis for the modern technology of refrigeration and provided both impetus and means for conducting scientific research at low temperature and very high vacuums. He developed a dimethyl ether refrigerator in 1874 and an ammonia refrigerator in 1876. In 1883, Svante Arrhenius developed an ion theory to explain conductivity in electrolytes. Le Chatelier's principles explains the response of dynamic chemical equilibrium to external stresses. In 1884, Hermann Emil Fischer proposed the structure of purine, a key structure in many biomolecules which he later synthesized in 1898. He also began work on the chemistry of glucose and related sugars. Alfred Werner discovered the octahedral structure of cobalt complexes, thus establishing the field of coordination chemistry. The most celebrated discoveries of Scottish chemist William Ramsay were made in inorganic chemistry. Ramsay was intrigued by the British physicist John Strutt, third Baron Raleigh's 1892 discovery that the atomic weight of nitrogen found in the chemical compounds was lower than that of nitrogen found in atmosphere. J.J. Thomson discovered the electron using the cathode ray tube. In 1898, Wilhelm Wien demonstrated that canal rays streams of positive ions can be deflected by magnetic field and that the amount of deflection is proportional to the mass to charge ratio. This discovery would lead to the analytical technique known as mass spectrometry in 1912. Marie Curie, a pioneer in the field of radioactivity and the first twice honored Nobel laureate, and still the only one in two different sciences. Mary Slowacka Curie was a Polish-born French physicist and chemist who is famous for her pioneering research on radioactivity. She and her husband are considered to have laid the cornerstone of the nuclear age with their research on radioactivity. Mary was fascinated with the work of Henri Becquerel, a French physicist who discovered in 1896 that uranium casts off rays, similar to the X-ray discovered by Wilhelm Röntgen. Marie Curie began studying uranium in late 1897 and theorized according to a 1904 article she wrote for Century magazine that the emission of rays by the compounds of uranium is a property of the metal itself, that it is an atomic property of the element uranium independent of its chemical or physical state. Curie took Becquerel's work a few steps further, conducting her own experiments on uranium rays. She discovered that the rays remained constant no matter the condition or form of the uranium. The rays, she theorized, came from the element's atomic structure. This revolutionary idea created the field of atomic physics, and the Curies coined the word radioactivity to describe the phenomena. Pierre Curie, known for his work on radioactivity as well as an ferromagnetism, paramagnetism, and diamagnetism, notably Curie's law and Curie point. With Henry Becquerel and her husband Pierre Curie, she was awarded the 1903 Nobel Prize for Physics. She was the sole winner of the 1911 Nobel Prize for Chemistry. She was the first woman to win a Nobel Prize, and she is the only woman to win the award in two different fields. Ernest Rutherford. Ernest Rutherford, discoverer of the nucleus and considered the father of nuclear physics, New Zealand-born chemist and physicist, Ernest Rutherford is considered to be the father of nuclear physics. Rutherford is best known for devising the names alpha, beta, and gamma to classify various forms of radioactive rays, which were poorly understood at his time. Alpha and beta rays are particle beams, while gamma rays are form of high-energy electromagnetic radiation. Rutherford deflected alpha rays with both electric and magnetic field in 1903, working with Frederick Soddy. Rutherford explained that radioactivity is due to the transmutation of elements now known to involve nuclear reaction. The observed results, Rutherford disproved the plum pudding model and concluded that the positive charge of atom must be concentrated in all small central nucleus. He also observed that the intensity of radioactivity of radioactive element decreases over a unique and regular amount of time until a point of stability, and he named the halving time of that is half-life. In 1901 and 1902, he worked with Frederick Soddy to prove that atoms of one radioactive element would spontaneously turn into another by expelling a piece of the atom at high velocity. In 1906, at the University of Manchester, Rutherford oversaw an experiment conducted by his students Hans Geiger, known for the Geiger counter, and Ernest Marsden. In the Geiger-Marsden experiment, a beam of alpha particles generated by the radioactive decay of radon was directed normally onto a sheet of very thin gold foil in an evacuated chamber. Under the prevailing plum pudding model, the alpha particles should all have passed through the foil and hit the detector screen, or have been deflected by at most a few degrees. However, the actual results surprised Rutherford. Although many of the alpha particles did pass through as expected, many others were deflected at small angles, while others were deflected back to the alpha source. They observed that a very small percentage of the particles were deflected through alpha angles through much larger than 90 degrees. The gold foil experiment showed large deflections for a small fraction of incident particles. Rutherford realized that because some of the alpha particles were deflected or reflected, the atom had a concentrated center of positive charge and of relatively large mass. Rutherford later termed this positive center, that is atomic nucleus. The alpha particles had either hit the positive center directly or passed by it close enough to be affected by its positive charge. Since many other particles passed through the gold foil, the positive center would have to be relatively small size compared to the rest of the atom, meaning that the atom is mostly open space. From his results, Rutherford developed a model of the atom that was similar to the solar system, known as the Rutherford model. Like planets, electrons orbited a central, sun-like nucleus. For his work with radiation and the atomic nucleus, Rutherford received the 1908 Nobel Prize in Chemistry. The first Solvay conference was held in Brussels in 1911 and was considered a turning point in the world of physics and chemistry. In 1903, Mikhail Tisvet invented chromatography, an important analytic technique. Robert Millikan, who is best known for measuring the charge on the electron, won the Nobel Prize in Physics in 1923. In 1905, Albert Einstein explained Brownian motion in a way that definitely proved atomic theory. Otto Hahn, father of nuclear fission and nuclear chemistry. Otto Hahn was a German chemist and a pioneer in the field of radioactivity and radiochemistry. He played a leading role in the discovery of nuclear fission and established nuclear chemistry as a scientific field. Hahn received in 1944 Nobel Prize for Chemistry for the discoveries. Nuclear fission was the basis for nuclear reactors and nuclear weapons. Niels Bohr. In 1913, Niels Bohr, a Danish physicist, introduced the concept of quantum mechanics to atomic structure by proposing what is now known as the Bohr model of the atom, where electrons exist only in strictly defined circular orbits around the nucleus, similar to rungs on a ladder. The Bohr model is a planetary model in which the negatively charged electrons orbit a small positively charged nucleus, similar to the planets orbiting the Sun, except that orbits are not planar. In the Bohr model, however, electrons orbit the nucleus in orbit that have a set size and energy. The energy levels are said to be quantized, which means that only certain orbits with certain radii are allowed. Orbits in between simply don't exist. The energy of the orbit is released to its size, that is, the lowest energy is found in the smallest orbit. Bohr later received the Nobel Prize in Physics for this work. In 1913, Henry Moseley, working from Vandenbroek's earlier idea, introduced the concept of atomic number to fix some inadequacies of Mendeleev's periodic table, which had been based on atomic weight. The peak of Friedrich Sordi's career in radiochemistry was in 1913 with his formulation of the concept of isotopes, which stated that certain elements exist in two or more forms which have different atomic weights but which are indistinguishable chemically. He is remembered for proving the existence of isotopes of certain radioactivity elements, and is also credited, along with others, with the discovery of the elements protactinium in 1917. In 1913, J.J. Thomson expanded on the work of Wien by showing that charged subatomic particles can be separated by their mass to charge ratio, a technique known as mass spectrometry. An American physical chemist, Gilbert and Lewis, laid to the foundation of valence bond theory. He was instrumental in developing a bonding theory based on the number of electrons in the outermost valence shell of the atom. Lewis' model equated the classical chemical bond with the sharing of a pair of electrons between the two bonded atoms. Lewis introduced the electron dot diagram in this paper to symbolize the electronic structure of atoms and nucleus, now known as Lewis structure. They are discussed in virtually every introductory chemistry book. Quantum mechanics. From the top, Louis de Broglie and Wolfgang Pauli, Erwin Schrödinger and Werner Heisenberg are the important heroes on quantum mechanics. In 1924, French quantum physicist Louis de Broglie published his thesis in which he introduced the revolutionary theory of electron waves based on wave-particle duality. In this time, the wave and particle interpretations of light and matter were seen as being at odds with one another, but de Broglie suggested that these seemingly different characteristics were instead the same behavior observed from the different perspectives, that particles can behave like waves and waves radiation can behave like particles. Broglie's proposal offered an explanation of the restricted motion of electrons with the atom. Austrian-born physicist Wolfgang Pauli developed the Pauli exclusion principle, which states that no two electrons around a single nucleus in an atom can occupy the same quantum state simultaneously as described by four quantum numbers. Pauli made major contribution to quantum mechanics and quantum field theory. He was awarded the 1945 Nobel Prize for Physics for his discovery of the Pauli exclusion principle, as well as solid-state physics, and he successfully hypothesized the existence of the neutrino. In addition to his original work, he wrote masterful synthesis of several areas of physical theory that are considered classics of scientific literature. In 1926, at the age of 39, Austrian theoretical physicist Erwin Schrödinger produced the papers that gave the foundation of quantum wave mechanics. In those papers, he described his partial differential equation, that is the basic equation of quantum mechanics, and bears the same relation to the mechanics of the atom as Newton's equation of motion, via a planetary astronomy. Adopting proposal made by Louis de Broglie in 1924 that particles of matter have a dual nature and in some situations act like waves, Schrödinger introduced a theory describing the behavior of such a system by wave equation that is now known as the Schrödinger equation. German theoretical physicist Werner Heisenberg was one of the key creators of quantum mechanics. In 1925, Heisenberg discovered a way of formulate quantum mechanics in terms of matrices. For the discovery, he was awarded the Nobel Prize for Physics for 1932 in 1932. In 1927, he published his uncertainty principle. Hence, the quantum mechanical methods developed in the 1930s and 1940s are often referred to as theoretical molecular or atomic physics to understand the fact that they were more the application of quantum mechanics to chemistry and spectroscopy than answers to chemically relevant questions. In 1940s, many physicists turned from molecular or atomic physics to nuclear physics, like J. Robert Oppenheimer or Edward Teller. Albert Einstein and Yuri Gagarin, for whom a chemical element was named during his lifetime. Diagrammatic representation of some key structural features of DNA. This heuristic approach triumphed in 1953 when James Watson and Francis Crick deduced the double helical structure of DNA by constructing models constrained by an informed by the knowledge of the chemistry of the constituent part and the X-ray diffraction pattern obtained by Rosalind Franklin. This discovery led to an explosion of research into the biochemistry of life. In the same year, the Miller-Urey experiment demonstrated that basic constituents of protein, simple amino acids, could themselves be built up from simpler molecules in a simulation of primordial process on Earth. This first attempt by chemists to study hypothetical process in the laboratory under controlled conditions helped kickstart bountiful research within the natural science into the origins of life. In 20th century, that is in 1970, John Popley developed the Gaussian program, greatly easing computational chemistry calculation. In mathematics and chemistry, every attempt to employ mathematical method in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. If mathematical analysis should hold a prominent place in chemistry, an aberration which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. Scope of chemistry. As understanding of the nature of matter has evolved, so too has the self-understanding of the science of chemistry by its practitioners. Chemical industry. The later part of the 19th century saw a huge increase in the exploitation of petroleum extracted from the earth for the production of a host of chemicals and largely replaced the use of whale oil, coal tar and naval stores used previously. Large-scale production and refinement of petroleum provided feedstocks for liquid fuels such as gasoline and diesel, solvent, lubricant, asphalt, waxes, and for the production of many of the common materials of the modern world such as synthesis fibers. Plastics, paints, detergents, pharmaceuticals, adhesives and ammonia as fertilizer and for other uses. Many of these required new catalysts and the utilization of chemical engineering for their cost-effective production. In the mid-20th century, control of the electronic structure of semiconductor materials was made precise by the creation of large ingots of extremely pure single crystals of silicon and germanium. Accurate control of their chemicals composition by doping with other elements made the production of the solid-state transistor in 1951 and made possible the production of tiny integrated circuits for use in electronic devices, especially computers. Thanks for Wikipedia. If you have done, please subscribe our YouTube channel.